right, a new three-part series here at Blue Glow Electronics. This series is focused on step-up transformers, otherwise known as SUTs, for moving coil phono cartridges. And part one of the video, which I'm putting together today, is primarily an educational video, which will teach you about step-up transformers and kind of how they work. And then we'll move to video 2, which will be focused on kind of reverse engineering. I found an old transformer in a piece of gear, and I'm trying to determine whether it would make a good SUT step-up transformer for the purpose of a moving coil cartridge or not. And then in the third video, hopefully we're going to build a SUT and actually see how the thing works out. So between the three of these, hopefully you'll learn a good bit about SUTs. Okay, pay close attention. You got to get this part. If you don't get this, the rest of this whole SUT conversation won't make any sense to you. What this is, it shows right here a coil of wire that is wrapped around some type of core material, and you're feeding this coil of wire with an alternating source, in other words an AC signal of some sort. And in most cases, when you're dealing with audio, it is a audio source here. And what happens when you feed it into this first coil, because this coil is wrapped around this core material, it induces, through this principle that Faraday uncovered years ago called mutual inductance. And what it says is EMF, electromagnetic force, induced into the secondary coil by the magnetic flux. See all these lines out here? These are lines of flux. Magnetic flux generated by the voltages and currents flowing in the primary. So what you induce here into this first coil gets transferred over to the second coil, not electrically, because if you read up here, these are two electrically isolated coils. They have nothing to do with each other electrically, but magnetically they do, because the core material that you're using in this transformer carries magnetic flux, and that magnetic flux induced into the first coil gets sent over into the second coil here, which causes a voltage of V2 based on what you feed into V1. Okay, and if you can grasp that concept, just a basic concept here, feeding a signal to the first coil because of the core material used in this transformer that carries magnetic flux easily, takes these magnetic currents to the secondary, feeds it, and you've got your secondary voltage. If you feed DC, direct current, into a transformer, you really don't induce this movement of flux, and you really don't cause anything to happen on the secondary. If you notice here, I said transformers work with alternating currents, AC voltage, and not DC. Another thing I noted here is transformers can have multiple secondary coils being induced by one primary coil. So you could have one primary coil here causing all this flux to flow within the magnetic core. And then you could have multiple secondaries like shown down here on this picture. See, we've got a primary, one of 120 volts here. We're feeding it in. This represents the core material. And then you're feeding out, say 10 volts here, 30 volts here, 50 volts here, because that's what's getting induced across into these secondary windings. So just keep that in mind. Okay, and I said here too, DC, the primary coil is seen as a big wire wound resistor, and nothing gets induced into the secondary coil. However, I did call out, this is this winding of wire into the in the primary and feeding DC into it actually gets used sometimes. So if you've ever built a push-pull audio amplifier and the output transformers, they actually use the kind of the DC resistance of this core here as the plate load and output tubes. But for the purposes of what we're dealing with step-up transformers, no DC at play. It's all AC. And typically a goal of a transformer here is used to achieve a different voltage on the output than what we fed onto the input. So V2, we want that to be different in some ways than what we fed into V1. So you can do one of two things. You can either feed into V1, let's say 10 volts, And on the output here, we would get 1 volt. That would be called a step down transformer. We have gone from 10 volts down to 1 volt. Or you could feed into V1 here with 10 volts, and on V2 here get out, let's say, 100 volts. That would be considered a step up transformers. And it says here output of V2 may be more or less than the input voltage. And if the output voltage V2 is identical to V1 here, then it gets termed an isolation transformer. And the purpose of that, you see them used a lot, is just to kind of electrically isolate the primary from the secondary. You see a lot of bench technicians use isolation transformers with 120 volts so that the main 120 volts in your house isn't the exact same 120 volts you're using when working on an amplifier. You can electrically isolate those and reduce your chance of becoming grounded by maybe stepping into some water or something and getting shocked or whatnot. And then lastly, transformers can also be used to transform impedances, and we'll talk about that a little more later. But there's this concept here of ZP, which stands for Z primary, and ZS, which would stand for Z secondary. All right, let's talk about some transformer nomenclature. So first and foremost, this would be the iron core, transformer core that you would see. And typically these things are made up of some type of laminated iron material that gets used. And what you'll have here is you'll have a wire wound around one side of this thing. And the number of times that you wrap the wire around is called NP, the number of turns in the primary. And then you'll have some number of windings here on the secondary part of this core. And if you'll notice here, there are more windings in the primary than there are in the secondary. And so that secondary would be called NS, the number of turns in the secondary. And then lastly, there's a figure typically called alpha or A. It is the turns ratio, typically seen as like 1 to 10, 1 to 20, 1 to 4, etc. So let me give you an example. Let's say there were 100 turns on this side of the wire, and there were 10 turns on this side of the transformer. Then this would be 100 to 10, or it would likely get simplified as 10 to 1. And typically you see that written as a 1 to 10 step up or step down transformer. And sometimes you may see it just referred to as a factor of 10. In other words, how many more times windings there are on one side to the other. It's a ratio at that point. Okay. And then you have here something called VP, the AC voltage fed to the primary. So if you put a connection to one of these wires and to the other, the voltage potential across those in AC would be your VP, or your primary voltage. And then your VS, the secondary voltage here, is what it gets induced across. You notice this green line here? You've got this magnetic flux flowing in this core, and it's actually what is causing the inductance over into this second core here. And there's a second coil and causing this voltage on this side. Then you also have something here called I primary. That's the current flowing through these wires on the primary. And I secondary, which is something that gets induced based upon the number of windings here, the number of windings here, and the effectiveness of this magnetic core here. And then it says magnetic flux, otherwise known as phi, is the flux linkage between the primary and secondary. And I said here, this is a big deal for SUTs. The better this transformer can conduct this magnetic flux, the better you get coupling between these two. The more of what's induced or fed into the primary gets induced into the secondary. And just for the record, the unit of measures for magnetic flux is in Webers. Okay, one other thing to note is that transformers, sometimes you'll see them represented on a schematic like this with some dots on them. And what these dots are showing is really, they're called phase dots. They are showing whether the input and the output match or whether they are out of phase. So let's say you wound this transformer with the windings going right to left around this core on this side, and then you've wound this one going right to left on this side. These things might be in phase so that the input, as it goes up, the output goes up, and as the input goes down, the output goes down. But if you wound this one right to left and this one left to right, you would get the dots out of phase. And hey, that's okay. You're still inducing the same voltage into the output. It's just as this one's going up, this one's going down. And as this one's going down, this one's going up. And what that would be represented as is 180 degrees out of phase with each other, the input is from the output. So just be aware of that when working with schematics on transformers and wiring them up. If you got these two wires reversed, then you would kind of get the same effect on the output as this. So let's talk a little bit about transformer core characteristics. If you'll notice this laminated iron core here that you see around the outside, and what it's got is you got coils of wire wrapped around here on the inside, and you certainly got your terminals to be able to connect your wires to and mounting tabs to hold this thing in place. But that outside laminated iron core, let's talk about some of the properties of it. First off, there's something called magnetic flux. We talked about that. That's the kind of the magnetic currents that flow here inside of this core. So the strength of the magnetic flux in a transformer is directly proportional to two things. First off, it is the number of turns of coil around the core in the primary, and the current flowing through the coil, something known as ampere turns. In other words, the amount of current you feed into the primary and the number of times the primary is wrapped around the core is what ultimately turns out to be what they call this thing called ampere turns, and thus magnetic flux is proportional to ampere turns. So the higher the ampere turns, in other words, the higher the current you feed this thing with and the more wraps it has around the primary, the more magnetic flux you will have flow. There's a term out here I'm going to use, but it doesn't get used a lot. It's called reluctance. So reluctance is kind of the magnetic equivalent to resistance. So in other words, if that core material here had a lot of reluctance to it, then it would have what you would consider in electrical terms as high resistance, and not a lot of current would flow through it. So what it's saying here is that a core with low reluctance, otherwise known as RM, has better flux transformer from the primary to the secondary, thus is more efficient. So if you have a transformer with a high reluctance value, you could think of it as having something with high resistance, which would not be as good as something with low resistance. The one thing you hear talked about a lot, which is kind of the opposite or inverse of reluctance, is something called permeability. And what it is the conductance of this core material. So items with high permeability are sought after for good transformer qualities. This is because a lower amount of MMF, magnetomotive force, it requires to establish flux flow from the flux flow from the primary to the secondary is required, thus a more efficient transformer. So the better materials that are used here in this core, the higher permeability that it has, the better job it does of carrying flux from the primary to the secondary. And so the more ideal the transformer becomes. And last but not least, alloys. Various metal types get mixed together or laminated together to create something called super alloys that have very, very high permeability. These are very often very expensive, and as a result of their complexity in manufacturing, yet they are highly sought after for really good quality audio transformers, whether they be in your SUT or whether they would be in your output transformers of an amplifier. Really good metal alloys that have a high permeability make for a great transformer, and typically they are very expensive as a result of this. So when I went through electrical engineering school, we learned a lot about this thing called the ideal transformer, because it was a way of modeling things in the classroom in an ideal state, and then figuring out how to apply those in the real world. But an ideal transformer, these are some of the characteristics about it. First and foremost, it would have zero winding resistance. In other words, no matter how many coils of wire you would have around the primary or secondary, there would be no resistance to that. That is, both of the coils of wire are purely inductive in nature, and they would have no resistive elements to them, which, as we all know, if you have a coil of wire, it has resistance. So there's no such thing as zero winding resistance. But for the better the transformer would be, the lower the winding resistance would be. So in some cases, you'll see in a step-up transformer, they may use a real high-quality wire like silver wire or something for the winding. It's certainly much more expensive, but what it does is it helps to lower this resistance. Up next, this ideal transformer would have an infinite permeability of the core. So, higher the permeability, the lesser the MMF it takes to kind of establish this flux linkage. That means if the permeability is high, less magnetizing current is required to magnetize the transformer core. In other words, the more efficient the transformer. So the higher the permeability you can get, the better typically. The third item here is no leakage flux. So in other words, all this flux that's flowing in this core, none of it would leak out, none of it would get lost, all of it would make it to the secondary. It is basically assumed that the entire amount of flux from the primary gets linked with the secondary, thus no leakage flux. That's a perfect world. That does not happen in the real world. That's why we have to be very careful in how we orient our transformers to each other, especially power transformers and output transformers, because they do leak flux, and that flux can leak over into the next transformer and induce some voltages there that you're really not wanting to see. It's a pretty big deal in audio output transformers. And then finally, we assume that they're 100% efficient. They do not have any losses like hysteresis losses, eddy current losses. So the output power of an ideal transformer is exactly equal to the input, thus 100% efficiency. And then I've got down here, guess what doesn't happen in the real world? None of these happen. But the closer you can get to any of these things, the better off your transformer is going to be. Okay, pay close attention here. So this is the meat of what we're trying to do. This is a step-up transformer. And if you notice a couple things about it, first off, we have a smaller input voltage than we do output voltage. And that is what we're trying to achieve here. In other words, a small little voltage coming out of our moving coil phono cartridge is going to be able to feed a larger voltage into the input of our phono preamp. And the way that gets achieved is by having more windings on the secondary than you do on the primary. So let's just make this up. Let's say this is 10 turns of wire, and let's say this is 100 turns of wire over here. And so what you would notice is that and let's just say this is 10 volts. So one thing to note, in a step-up transformer, the winding ratio is directly proportional to the voltage ratio. So if we had 10 volts fed into this thing, and we had that via 10 turns on the primary, and in the secondary, if we had 100 turns, guess how many volts you would have? You're exactly right. You would have 100 volts here into the secondary. The same scenario would play out if this was 1,000 volts. All of a sudden, if this was 10 windings here and 100 windings here, if this was 1,000 volts, you would have 10,000 volts here on the output. So the The number of turns ratio is directly proportional to the voltage ratio. Now, there's an interesting phenomenon that takes place, and that is we multiplied our voltage here by 10 because our ratio of N secondary to N primary was 10, right? This little A, remember here we talked about earlier, A would equal to 10. Well, one thing I didn't tell you about is that the current does kind of the inverse. So if we had fed this thing on the primary with 10 amps of current, so if that was 10 volts at 10 amps, on the secondary over here, we would have gotten out 100 volts at 1 amp. So it's just the opposite. As you're multiplying voltage, you're actually dividing current. So in other words, you're giving up something to get something. So 10 volts in, give you 100 volts out. If this 10 volts took 10 amps, it would feed out 1 amp. But that's not a problem for us, and you'll hear why more here in a minute. Okay, same concept here, just kind of the reverse. You've got more windings on the primary than you do the secondary, thus you feed a larger voltage in here on the primary. You get a smaller voltage out here on the secondary. So let's just say we were feeding this in with 10 volts, and if this had 100 windings and this had 10 windings, guess what the voltage is out over here? 1 volt. You're correct, because this ratio is 100 to 10, otherwise known as 10 to 1, and it's kind of a multiplying factor of 10, but we're not really multiplying because we're stepping down, so it goes from 10 to 1. But let's just say this was at 2 amps on the input. Guess what you would end up with on the output here? You would have went down by a factor of 10 on voltage, but you would have went up by a factor of 10 on the current. So you would have had 20 amps here on the output. So all in all, you're trading one for the other here on the input and output. But there again, not a big deal for us. So you could probably deduce this on your own based on what I've just told you, but there's a transformer power equation. And it says if the transformer is 100% efficient, which we know in the real world that's never the case, but if it was, then, and we know that power equals to current times voltage, and remember a while ago when voltage went up, current went down, when current went up, voltage went down, then current in the primary times voltage in the primary is equal to the current in the secondary times voltage in the secondary. Thus, power in the primary is equal to power in the secondary. So if you double the voltage from primary to secondary, then you half the current. If you half the voltage from primary to secondary, you're doubling the current. So the power stays the same on both sides. Okay, most of you are kind of familiar with the term resistance. If you've done anything with Ohm's law, it's one of the primary factors used there. But there's a term out here called impedance. And I'm going to stay away from going way deep into impedance. But I can show you how to work with it without going into the physics and math behind it. But basically, your input here would have a primary impedance, otherwise known as ZP, and your secondary here would have something known as the secondary impedance, otherwise known as ZS. But it's basically, impedance is kind of a combination of capacitance and inductance, as seen by the device feeding into this, and as seen by devices that are feeding from this thing on the output. And so if you'll notice up here, we talked about this earlier, the voltage transformation ratio. Remember, if you had 100 turns here, 10 turns here, so you would divide 10 by 100, you'd end up with a ratio of 1 to 10. Same with current transformation ratio, number in the secondary divided by primary. But it gets a little more complicated with impedance. the primary turns divided by the secondary turns is equal to the square root of the primary impedance divided by the secondary impedance, otherwise known as NP over NS is equal to the square root of ZP over ZS. And I thought about it long and hard, and I thought, well, I could try to teach all this math, but I'm going to try to stay away from that. And instead, I'm going to take you over, and here's a link here, and I'll put this in the notes below on the video. You can actually click on this. Okay, it'll actually take you to this website that I had the link for there in the video. And then what it has is an impedance matching calculator. So you can look at the primary impedance here, the secondary impedance. You just have to know the number of turns in the primary and number of turns in the secondary. It showed you that same formula I did before, but it gives you a neat little device calculator here you can use. And basically, let's just pretend the primary has 100 windings and the secondary has 1,000. Well, we would know that the turns ratio then is 10 or 10 to 1. And if we know that the secondary, which this is almost always the case, when you're feeding into the moving magnet RCA input of a phono preamp that has RIAA kind of characteristic to it, then the number we typically work with 99.9 times out of 10 out of 100 is 47,000 ohms is the secondary impedance we're trying to match to. So if you key those three in and click calculate, it'll come back to you and say, hey, your primary impedance that will be seen. So in other words, if your secondary impedance is known, and that would be known because it's the it's kind of the load here in the RIAA circuit here of the first preamp stage. If you know your turns, you know your secondary turns, and you know the impedance here, then it'll help you calculate that, and it's 470 ohms. Well, what if we were using, instead of a 10 to 1 step-up transformer, what if we were using a 20 to 1? Well, you could click calculate, and it would help you see that the impedance seen by the primary is 117.5 ohms here. So you've got to be able to do squares and square roots to be able to calculate this stuff, or you can use this simple little calculator here. So let's talk about a little more practical now. What does a step-up transformer do? It kind of serves two purposes in the real world. The first thing it does, its primary function, is to step up the voltage from the primary here of a coming out of your cartridge. If you're using a moving coil cartridge, that is a very, very small signal leaving that cartridge coming into your SUT. So it's primarily designed to step that voltage up into the first stage of a moving magnet phono stage. And in this case, I stole a picture of a little bottle head unit. And then the second part that it does is it actually loads the cartridge up properly. This cartridge is designed to work with a proper load across its output. And so if you can achieve both of those, the proper cartridge loading and the proper amount of voltage gain step up here, then you've got the right step-up transformer for your system. And I thought I'd talk just a little more about where step-up transformers, step-down are used. So between your power amplifier here, these things typically have two output transformers, and they are typically matching impedance between here and your speakers, as well as they're typically a step-down transformer, believe it or not, that's being used in these, because you'll typically have about 600 volts, maybe 500 volts on the plates of these tubes. And by the time it gets stepped down to feed your speakers here, you might have anywhere from 20 to 30, 40 volts sitting on the speaker leads, as well as it is doing what I call power matching. It's very important that all the power here in this thing, both current and voltage, get transferred to these speakers as much as possible. Over here, we're not really worried about current. We're worried about voltage. This voltage coming out of a moving coil cartridge is too light to drive the inputs of these tubes right here. Thus, you would get a low volume throughout the entire system. So why would I use a step-up transformer? Well, first and foremost, moving coil cartridges, otherwise seen a lot of times as MC cartridges, are considered superior to moving magnet cartridges, otherwise known as MM cartridges, by many audiophiles. And you notice my big asterisk here. Like anything with audio, that is a very subjective statement. People will argue that all day long. I will tell you there are good moving magnet cartridges out there. I run the Orthothon 2M Black on several of my units. It's a fairly high-end moving magnet, and I think it's better than most moving coils that in the same price range. But I think you can also get a really good moving coil cartridge that'll blow away most moving magnet cartridges, including that 2M Black. But you may put a lot more money into it. You can if you wanted to, you can spend 10 grand on a moving coil cartridge easily. These things can get quite expensive, and whether they're worth all that, that's subject to debate. So here's the reason why you need a step-up transformer, though. If you're going to run a moving coil because you believe it's superior in some way, or you just want to try it out, moving coil carts produce about a 20 dB, or otherwise known as 10 times lower output than a moving magnet cartridge does. So typically 0.13 to 0.5 millivolts. That is teeny. That is a little bitty, itty bitty signal. Hardly anything. Whereas a moving magnet is 5 millivolts to maybe 1 volt, in that range. So this is the real reason. Building a phono preamp that has good quality and low noise figures for a moving coil input is very difficult to do. In other words, that signal is so small that when you're trying to build an amplifier to amplify that little bitty signal, it is so easy for noise and interference to get in into those gain stages. It's tough to do. So those that are done right are typically expensive, especially true for tube phono stages. It is very hard to build a moving coil tube phono stage that doesn't introduce some type of noise or interference along the way. So if you can use a passive device like a transformer to step the voltage up to a level that's then easier amplified without all this noise being induced, you may be better off. That's why you might want a SUT. And as I mentioned before, an SUT basically increases the voltage level output of a moving coil cartridge to the level of a moving magnet cartridge so that a moving magnet phono preamp can amplify the signal. And a good SUT will also help load the moving coil cartridge properly if done right. Alright, so some characteristics of step-up transformers. Most have either a 1 to 10, 1 to 20, or 1 to 30, something in those ranges. It could be 1 to 9, or 1 to 17, or 1 to 28, but something close to 1 to 10, 1 to 20, 1 to 30 turns ratio. Some of them will have multiple secondary taps, so you'll see some that have 1 to 10 and 1 to 30, giving you multiple options. They match the load cartridge impedance properly. So one thing, if your cartridge has a load impedance of say 100 ohms, then typically you want the input impedance here of your SUT to be 10 times that. So you'd want it to be 1,000 ohms. But I'll give you a good example down here. The typical RIAA input specs for a moving magnet phono cartridge stage is 47,000 ohms, as we mentioned earlier. So a 1 to 10 SUT, using the input impedance formula, input equals output divided by that turns ratio squared. So 47,000 divided by 10 squared, or divided by 100, would equal to 470 ohms that the cartridge would see looking into the SUT. So typically your output impedance of the SUT would be 47,000 ohms, your input impedance would be 470, and typical internal source impedance of a cartridge is usually between 10 and 50 ohms, and you want this second impedance here to be 10 times more than this first, than the impedance of the card itself for maximum voltage transfer. So some of you who have done any electrical engineering work before would say, hey, I thought you would want to match impedances perfectly. So if you had 10 ohms on the cart, you would want a 10 ohm input impedance. Well, that is a true statement for maximum power transfer. That is not a true statement for maximum voltage transfer. And that maximum power transfer, you may be willing to give up the voltage by gaining the current, which in this case does us no good. The SUT game is all about voltage gain. So you're going to want this thing to be about 10 times what your typical load is over here. Otherwise, you start trading off that current for voltage, which is not what you want. All right, so what makes a really good step-up transformer? So I talked about having those multiple taps, maybe 1 to 10, 1 to 20, 1 to 30. They load your cartridge properly. They have a flat response across the entire audio frequency range. And the way you figure that out is you typically feed the input of a SUT with a square wave and kind of examine the output. You will see minimum ringing and a very flat response in a very good step-up transformer. A good step-up transformer will utilize some type of internal electrostatic shield. It's kind of a form of a Faraday cage that typically gets grounded, so you'll have a wire that goes to ground. And then you would also see minimal phase shift from the input to the output. So if you fed in a sine wave on the input and then compared it to the output, you wouldn't see a whole lot of phase shift between those two in a very good SUT. And then probably the most important factor in a good SUT is high permeability of the core material. This is why old Altec, Peerless, Fairchild, Western Electric, EMT, Partridge, Triad, Perma-Alloy, etc. transformers are so highly sought after and valued. I'll give you an example. A set of Western Electric 618B step-up transformers. They were originally designed as input transformers on some old Western Electric amplifiers. But if you happen to find a pair of those and pull them off, those cartridges will sell usually between $2,000 and $3,000 a piece. So you could build a step-up transformer that would be worth $5,000, $6,000 at that point in time. Same with some of these old Fairchild or Partridge, some of the Triads. They're just insanely expensive because of the really good materials that was used. And what I said here was the amount of research, engineering, and cost of material development that went into these things back in the day just isn't so feasible these days. A lot of the materials used back then aren't mass produced today due to cost and availability. So there's always some trade-offs these days, it seems like. And I'm not saying you can't get good stuff these days. You can. There are people that make good step-up transformers these days. They're just not inexpensive because they're having to use very high-priced alloys that are very low production, and it's the whole supply and demand thing. They're just very expensive. So even a brand new step-up transformer that has really good permeability in the core, that could still be $1,000 or more device just because of the low production quantities. If you remember earlier, I talked about feeding the primary of the SUT transformer with a square wave and then watching it on the output. Well, if on the output you see something that looks like this is called ringing. In other words, there's an overshoot and then kind of a compensation for that in the transient here. And finally, it settles back down to normal. So you would want to try to minimize this dampening. And there's some techniques that I'll show you how to do that with. And you want to try to get this. This would be a good example of a dampened signal here. You've kind of rounded out this transient ringing here. By the use of a proper loading resistor, and we'll show you that here. And you can follow this link as well. By the way, this is one of the links I'm going to share with you, this Rothwell. It's an excellent explanation of how moving coil transformers work. And you can see there's a lot to it and there's a lot of math involved. And I was trying to simplify this video and not get into all this math. But a couple things, you can kind of see here the ringing. And you can see how this square wave has some slope to it. It's not perfectly flat. And you can see here they're trying to cut off this ringing by loading the output. See, this was the original 47K load. Here they're trying to load it with 22, which gets it a little better picture. And then here they loaded it with 10K and it's looking pretty good. And then they loaded it with 5.1K and it looks great. The problem with figure 1D over here, if you'll notice that this thing was a full bar here of gain or more, you start to knock down the overall gain of this thing when you start to play with the load resistors on these SUTs to get rid of the ringing. So there's just like everything in electronics, there's a trade-off. You can get rid of the ringing, but then you've got lower gain. And you can see some more examples here, ringing, ringing, ringing. Hey, they finally got it looking great here. And this is a beautiful one. It's flat, but as you'll notice, look at the gain. It only goes up to right here. You'll notice over here where we started, you had a full bar here of gain. And it kind of goes into showing, you know, this is a pretty good optimized load here, whereas this over here has got some a little bit of undershoot and then it's building back up. It's not the correct load for this thing. So this is where it even gets more complicated. These are a couple really common, and by the way, this HANA EL is a card I've got on order. I am dying to try one of these out. I'm reading really good things about them. I've had the Dynavector 10x5 before. Can't say I've had a lot of Denon 103s. I have on some customer units, but I've never personally owned one myself. But take a look at this. You've got a couple different things going on here when you start to look at their specs. This one has an internal resistance impedance of 30 ohms. This one has 40 ohms, and this one has 150 ohms. Okay, so 3 different moving coil carts, very different values. But then they're suggesting, remember, typically you want 10 times the loading. So they're saying here, hey, this one's 30 ohms, but we suggest a 400 ohm load. This one's they're saying, hey, we suggest 100 ohms minimum, probably more like 400 ohms because you want to be 10 times this. And this one here is saying, hey, our load resistance is 150 ohms, but we would recommend, our DC resistance 150, we're recommending greater than 1K ohms. So 400 ohms, 100 ohms, 1K ohm. A lot of variety here in what we're seeing. And I thought I'd take you to this website and show you a little bit about that. Okay, I really like this website. It's mh-audio.nl, and the link I'll put below. But it does some of what I did. It talks to you about what are step up, what are step downs, what are, is a unity transformer. It talks about moving coil cartridges. Goes through the same stuff I went through, number of primary, secondary, da-da-da. But then instead of getting into a lot of math, it actually gives you some calculators. So here it talks about some pretty common cartridges that are out there and their characteristics. But then it has a series of calculators here. So let's just say your moving coil output puts out 0.15 millivolts. And your moving magnet has 5 millivolts, and you wanted to calculate the gain required. Look, you would need a multiplication factor of 33. So a 1 to 30 transformer would work out well for you because you need a gain factor of 30 dB here. It also helps you calculate loading. So if you know the phono stage is 4700 ohms, and let's just say you were using a 20 to 1 transformer, you could click calculate here and it would tell you that your gain is going to be 26 dB, and the input impedance of your SUT would be seen as 117.5 ohms to the cartridge. You could change this to 10 and I'll guarantee you that changes down to 470. Yep, it's just the simple math here that we did earlier. And then finally, it shows you here about resistor tuning. So resistor tuning is when you put a resistor in parallel with the secondary of the coil on the SUT. In other words, to to work in parallel with the 4700 ohm load resistor, which ultimately reflects back a different impedance to the cartridge itself. So let's say we had a phono stage of 4700 ohms, and let's say like that one cartridge, it wanted a 100 ohm load on it, and we were using a 1 to 10 step-up transformer. You do calculate, and it would tell you then that you need to put in a 12.702 ohm resistor in parallel here to properly load that cartridge at 100 ohms. And you can see the math and how that's done over here. And then if you knew the 12.702, you could come down here and do a search, and it'll tell you, hey, the closest EIA value is either going to be 1500 ohms or 12.7 ohms if you get an E48 EIA standard resistor, which is probably close enough for what you would need here. So excellent website at helping you figuring out some of this loading. And some of your higher end SUTs would have a little click turn switch in it that would let you switch in or out multiple resistors here to try to better match cartridges. Okay, I thought I'd just show you an example here of a one of these units with the the top on it and top off. So if you'll notice one thing here on it has for this grounding lug, it has a switch that either goes to left and right or just ground. And you can kind of see how that plays out over here, where you'd have it just to the center lug, or you can go left or left plus right here. In other words, bridging these two together. Sometimes the grounding on these things sounds better one way than the other. Similarly, you could have high and low gain here. In other words, if this thing had both a 1 to 10 step up and a 1 to 20 or 1 to 30, it would let you switch on each side. And then this is designed to plug into it a 4722 Alltech Peerless transformer. And last but not least, I'm going to leave you with some good sources here. The analog department, Rothwell, K&K Audio up in Raleigh, not far from me, Bob's Devices, Vinyl Engine, Six Moons, MH Audio, which we looked at, and then a transformer impedance calculator. All these are great, and I'll put them into the section below so you can look them up. But I hope you learned a little bit about step-up transformer. Keep in mind, the ultimate goal is step the voltage up coming out of a moving coil cartridge to the level that would be coming out of a moving magnet cartridge is ultimately what you're after, and you want to do that with the best frequency response. In other words, carrying all your frequencies from the primary to the secondary and having the most efficient transformer that you possibly can, and doing that is the entire goal. Stay tuned, part 2 will be coming soon.